Okay, I think it's recording.
Okay, Nick, do you want to kick us off?
Yeah.
Or should we wait for more people?
Who's on? So Matt's on a plane. Art, I assume, is traveling.
Yeah, we can probably get started.
And DFX call.
Okay, yeah. Audition. Okay, I'll just kick us off so we don't end too late. Okay, welcome to another internal learning session. Today we're going to talk about the cross, and we're going to look at the technical implementation and discuss some design trade-offs and some other discussions, talk about future versions, and talk about what exactly we've implemented so far, like what we'll be deploying this quarter. So we all know that the gas prices are too high and that the L2s are going to be a big part of the scaling future. So part of our thesis is that L2 liquidity will continue to increase, and there will just be this really stable total addressable market for L2 to L1 bridges. And this liquidity will continue to increase. So the number one problem is that you currently are stuck on L2 for 7 days while you wait to exit. And this is because of the way optimistic rollups work, in that you need to give validators time to check all the transaction proofs and make sure that the merge back from L2 to L1 is correct. And this default time might decrease. I don't think it's going to decrease by too much. It probably won't decrease less than a day. So there will, for the foreseeable future, there will be a need to exit quickly. And the meta goal for UMA is also, we originally wanted to demonstrate how the optimistic oracle is it's not just a price oracle, it's just a general insurance mechanism. We can use it to prove just any complex statement, and this is the first good demonstration of how you can prove statements across chains. So you can prove L2 actions and secured by an L1 optimistic oracle. Chris, do you want to start going?
Sure. So, like Nick said, like the goal of the optimistic oracle and a cross is to make a proof around a statement on L2. So something happened on L2, and then using that, make a decision on L1 to do something else. So that's, in the case of what we're building here, is to actually fulfill an exit from the L2 back to the L1. And what we'll see later on when we talk about future versions, like you can do this for more than just bridging transfers. But for now, we're kind of keeping the scope fixed on bridging between L2s and L1. Yeah, we can use this to do some quite sophisticated things, which we'll get to now. So the basic structure of what we're going to go over now is how a cross kind of acts like a 1 week loan. So when we exiting from L2 to L1, like Nick mentioned, there's this delay that you have to wait. And basically what a cross lets you do is take your withdrawal transaction from the L2 back to the L1 and effectively sell that to someone else for a fee. And you can think of this as a loan. So liquidity providers will effectively buy that withdrawal, and they'll give you instant liquidity on L1 in exchange for a fee. And it acts kind of like a loan in the sense that there's like an interest rate, which is a function of, utilization or some other metric. And at the end of that 1 week period, the liquidity provider gets paid back and the withdrawer gets instant liquidity. And obviously the depositor is happy to do this because they receive funds instantly, and the liquidity is happy to do this because they don't need instant access to their funds. And they obviously get compensated in the form of a fee. And we'll see how these cash flows are structured in a bit. So to start off looking at the contract architecture, this is a basic overview of how the contracts are structured on Ethereum L1 and L2. The vast majority of the complexity and the logic sits on ETH L1, and the stuff that's actually on the rollup is pretty minimal. So we'll start looking at ETH L1 and kind of work through the contracts just to explain what's going on. There's not a lot of moving parts. So on the extreme left, we've got the DVM and the optimistic oracle above that. And those are two components that you guys should be pretty familiar with from the LSP, as well as other products that use the optimistic oracle. We then have like a bridge admin, which is owned by the DVM, and that gives the DVM and therefore UMA governance controls over certain governance actions that the bridge might need to do, such as whitelisting tokens or changing governance parameters on the L2 side. We then create a liquidity pool, which we call a bridge pool, for each kind of token that Across supports. So in this example, we have an UMA pool, a WETH pool, and a USDC pool. And the idea basically is that each piece of liquidity can be pooled based off of the native token, and then that can be accessed by n number of L2s. So in this diagram, we just have Optimism L2, but we could also have like Arbitrum and any other like rollup that comes into the future can all access the liquidity. And then on the L2 side, we have this bridge deposit box, and the basic idea is that that's where users will deposit funds, and then they get paid out from the liquidity pools on L1. And we'll get into the cash flows a little bit later and how that all fits together. The piece at the top of this diagram, sorry, Nick, is the canonical Optimism token bridge. So Optimism does provide a bridge for moving back from L2s to L1. The problem though is that this is where the delay is. That's the component that has the 7-day lockup, and that's the piece that we're trying to optimize around. So yeah, if you guys remember from one of our previous internal learning sessions where we discussed some of the trade-offs on these layer 2 solutions, I think it was in the Polygon discussion, we spoke about how getting into the L2 is very quick. So getting from ETH1 to Optimism is like a 5-minute process, but it's the exit that's slow, and that's the canonical bridge that we're working around. And in the context of the 1-week loan that I mentioned earlier, the payout that the liquidity provider gets, that effectively is flowing through the canonical token bridge, which we'll get to in a bit when we look at some of the cash flows. Okay, you can go to the next slide. So I thought this was like a triple layer pun, was pretty good. Okay. So there are two kinds of relays that Across supports. We have a slow relay and an instant relay. We're going to start off with the slow relay because it's easier to understand, and it also fits more cleanly within the framing that the optimistic oracle has been used in different contexts. So the basic flow consists of 3 main steps. First, a depositor will add funds into the deposit box on L2. And this is literally like a deposit transaction that they submit. When they do this, an event is emitted, and then at which point a relayer will detect this, and we get to point B, where a relayer brings this information onto L1. And effectively what they're doing is making a state claim about the status of that L2 deposit on L1 to the optimistic oracle. And if that proposal passes the liveness period, then by definition it's valid because it wasn't disputed, and then we can pay out the disputer, or pay out the relayer and the reward and the cash flow to the depositor. I think there's a typo in the slide, but yeah, we can ignore that. We'll get to the instant relay a little bit later. I've got a diagram on the next slide that kind of showcases this in a bit more of a visual way. So I've also included here the actual like function interfaces so we can see what's going on. So 1A is the user sends a deposit, and we can see some of the information that's provided here. So we've got the recipient, L2 token, the amount, and then 3 variables that are to do with fees. And we'll get to fees a bit later. And I think it's important here to note that L2 is the L2 token is definable. So this means that we use the same deposit box for n number of L2 tokens, which keeps things quite simple and clean, and overall just generally like simplifies the interface for the depositors. We then produce this event, and that basically just contains all the information that was included in the deposit transaction. Then on the other side of that dashed line, when we're on ETH L1, the relayer monitors for those events. And then when they see that one of those events was emitted in the deposit box, they then call the relay deposit method. And they basically like claim all the information that was in that event. So all the parameters that are in that method are basically the exact parameters that were emitted in the event. We then go to the optimistic oracle and we say, on the price identifier, is cross-chain relay valid? We basically take all that data and put it into the ancillary data in the price request. And we ask the optimistic oracle, is this bridge transfer valid? And then in the same transaction, we propose the price of 1. So we're saying, basically making a claim that this data is valid. And then a disputer, if they think it's invalid, they'll then come and dispute that claim, saying that it's invalid. You can go to the next slide. So this is what happens after liveness. So after the optimistic oracle liveness, if that proposal that the relayer made was not disputed, that means that the claim that they made around the L2 state on L1 is true, and we can then actually finalize the payouts. So we call the settle relay method, and we feed in the deposit data, which is basically the stuff we looked at earlier in that method's parameters. And you can follow the cash flow there by looking at where the USDC symbol is. So the recipient will receive their deposit amount minus a relayer fee and minus an LP fee. And then the relayer will get a reward and the LPs will get a reward. You can go to the next slide. So then we look at the instant class of bridging actions. So the bridging action, when it's instant, is very similar to slow, except there's this additional step where we speed up the relay. So again, someone deposits funds on L2, someone brings that information onto L1 and makes a state claim to the optimistic oracle. So those points A and B are the same as in the slow case. And then C is where things change slightly. So a relayer can then speed up the relay by instantly finalizing it. So what this means in effect is that the relayer fronts all the capital that the recipient would receive, and they pay it out effectively instantly. If the optimistic oracle proposal then passes liveness, then instead of paying the recipient of the deposit, we pay back the relayer, because the relayer basically like fronted the capital, and then in that case we actually repay them rather than the recipient. Go to the next slide. So here we've got the second part of that first diagram that we had. So this is just the stuff on L1. Everything on L2 with the event is the same. And the only difference here is that we now use this thing called multi-caller, which basically lets us call two methods at the same time. So we first call relay deposit, and then in the same transaction, we call speed up relay. So basically the logic that the relayer will have internally is it'll consider, given the fees that the depositor specified, what is the most profitable action for me to do? And if it's the most profitable action is to do an instant relay, then it will first relay the deposit and then speed up the relay. And everything else with the optimistic oracle remains the same. The difference though is the user is now instantly paid out rather than having to wait the liveness of the optimistic oracle. So it's a trade-off of, you know, getting the funds within like a minute of depositing on L2 versus having to wait maybe 2 hours for the optimistic oracle liveness. And the downside from the depositor's perspective will be a slightly higher fee, which we'll get to in a bit. So you can go to the next slide. So what we can see now, when this relay settles versus the previous one, the only cash flow here is to pay back the relayer. So we don't need to pay anything to the recipient because they actually got paid out instantly when the instant relay was finalized. And rather, we just pay back the relayer the amount that they fronted for the capital to the recipient, plus the instant relayer reward. So one part that we haven't really discussed is how do we get funds back from L2 onto L1 after the 7-day interval over the canonical bridge. So the basic structure that we have behaves the same on both a slow and a fast withdrawal. And in effect, the way it works is after a period of time of deposits on L2, we basically bundle up a set of deposits, and then we send a withdrawal over the canonical bridge from the bridge deposit box, which is the thing that people are sending money to on L2. We send the currency through the canonical bridge back to the bridge pool. And the reason we bundle funds together is because that bridging action is actually quite expensive. So if we can group, n number of transactions in the same batch, then it becomes much cheaper. And the way that we prevent people from spamming this is we effectively just have like a delay on how frequently bridgings can go from L2 to L1. So you can imagine, like in the USDC pool, we'll say like maybe once every 6 hours at maximum, we can move funds from the L2 bridge deposit box over the canonical bridge to the bridge pool. Anybody on L2 can call that bridging method. There's no restriction on who can call it. And that's just because there's like multiple actors that might want to do this. Arguably, relayers might want to call it, or LPs might want to call it, or maybe UMA wants to call it in the beginning. We haven't baked in any like rewards for calling that method. There's no like percentage fee, so it's not an incentivized call, but we think that's okay for now, and we can always improve those mechanisms later. And then on the L1 side, the way that withdrawals from Optimism work over the canonical bridge is effectively once the 7-day liveness has passed, you generate a proof, which you then bring on chain. And if that's validated and enough time has passed, then the tokens are sent from the bridge back to the recipient. And in this case, they would go to the bridge. We do a little bit of internal accounting in the bridge in the bridge pool to actually correctly update the balances, but we'll get to that a little bit later. Okay, you can go to the next one. Okay, so let's briefly talk about fees. Actually, before we do that, are there any questions? I just went over like a lot of content pretty quickly. So before we go into fees, does anybody have any questions?
What happens if there's a hack in the time between you've paid out, but you're still waiting on things going across, or if there's a hack in the fast withdrawal until the liveness period ends?
When you say a hack, do you mean like UMA's contracts get hacked or the L2 gets hacked?
No, I mean like the token itself gets hacked and falls drastically in value. Or
yeah, that would be bad. And I guess like the LPs would just take on a lot of price risk in that case, and they would probably start pulling out their funds from the pool. But in the beginning, I mean, we're only really going to be listing like blue chip currencies, like probably some stable coins and wrapped Bitcoin and DAO tokens. So hopefully that doesn't become too much of an issue. Like we're not going to be really bridging many shitcoins. I'm not sure if anyone else has a more input on that. Maybe Hot?
Well, no, Chris, I was just going to ask, would that be equivalent of just like take Compound and one of the assets that is that you can deposit on Compound kind of getting hacked? Would it be the equivalent sort of risks?
No, I don't think so, because our pools are isolated. There's no cross-currency risk the way that there is in Compound.
So it's actually less bad than Compound, right?
Much less bad.
Okay.
Yeah, it's
So,
like a Kashi money market where they're isolated lending pools.
okay, so Vari, just to reiterate that, like in Compound, if one of the deposit assets gets hacked, and let's just say you can print, like gets broken, so you could print infinity of it, you can drain all of Compound. So Compound has to be very specific which assets it lends to its platform. And what Chris is saying that if one of the assets we lend to our platform does turn out that somebody could print 1 billion of it, it's very bad across for that pool, but it would not affect the other pools. Is that right, Chris?
Yeah, and I also don't think it's necessarily that bad, because we don't really consider the value of the currency anywhere. Like there's no notion of margin. At no point do we care about the price, right? So as long as it remains like 1 token equals 1 token, if the token is worth 1 cent or like 0, it doesn't change the function of that particular pool. So
Well,
I don't.
it's very bad for that protocol or that project, but we're agnostic and
For
we
sure.
did nothing wrong.
Yeah.
Right.
In the scenario where there's like a lot of volatility and maybe the LPs want to withdraw their funds, are they able to do so if there's a bunch of fast relays that we're still waiting to pass liveness, or are they restricted until after that liveness period? Like, does the fast relay take on a risk of not getting their money back within 2 hours, assuming that there are no disputes?
Yeah, so there are 3 different variables that we track regarding utilized liquidity. There's liquid reserves, which is funds that can be withdrawn by the LPs and is available for bridging. There's utilized reserves, which is funds that are moving between L2 and L1 that are basically in flight, waiting the 1 week liveness. And then there's pending reserves. And pending reserves are the ones that cover the case that you just mentioned, which is like a bridging action has started, but it hasn't no funds have actually flown out of the pool yet. So they're pending in the sense that they're like booked off for the finalization of either a slow or an instant relay. So because we bookkeep those 3 variables separately, what that means is there's never a scenario where a relay that's brought onto L1 can't be finalized. We check at the point of relay that there's sufficient liquidity to finalize both an instant and a slow relay. And that does mean, though, like LPs might not be able to withdraw until those relays have come through the bridge, just as it is in compound when there isn't sufficient liquidity to withdraw your money.
Are LPs able to set aside some of the money in flight from L2 and say like, hey, like I do want to get out of here at some point, like please stop utilizing, my funds? Like,
no, it'll be first come first serve. So as soon as the funds land on L1, you must withdraw basically. But the same like race condition holds for more relays coming in, right? So as long as you withdraw before the next relay comes in, you should be fine.
All right.
Okay. Okay, so if there are no other questions, then we can actually talk about the fees. So yeah, Nick, just go back to the previous slide. Okay, so there are 3 main kinds of fees that a cross has. There's the slow relayer fee, an instant relayer fee, and a realized LP fee. So the slow relayer fee is paid to that initial relayer who actually brings the information from L2 onto L1. And all this fee is specified by the depositor at deposit time, as is the instant relayer fee. The instant relayer fee is very similar to the slow relayer fee, except it's paid to the depositor or the relayer that speeds up a slow relay. So this could be the same person that actually did the slow relay, like we described in the diagram before, where the relayer is calling slow relay and then instantly speeding it up in the same transaction. So in that case, they would receive both of these fees. If a depositor doesn't want an instantly finalized relay, if they're happy to wait the 00 liveness, then they can just set the instant relay fee to 0. And in that case, they will only get the slow relayer fee because no relayer would instantly relay something that they don't get paid for. The realized LP fee is a percentage of the bridged amount that gets set aside to the LPs to compensate them for the liquidity that they provided for that relay action. And this is obviously paid out pro rata to liquidity providers as a function of how much liquidity they've added to the pool. And we'll get into how that works a little bit later, but basically it's calculated off-chain by relayer bots and is verified by the optimistic oracle. We'll get into the details in a couple slides on that. Okay, you can go to the next slide. So the fee model that this realized LP fee uses is very similar to Aave in the sense that it's a function of utilized reserves versus the total pool liquidity. And from that, you can calculate basically the cost of a loan in an APY. In our model, we take that APY and then convert it into a 1 week, an equivalent of like a cost of a loan over 1 week. The way that this works in implementation is that when the depositor actually sends their money on L2, they specify a quote timestamp. And this is basically a timestamp where they say, I'm happy to pay the LP I'm happy to take the utilization at this timestamp as the amount that I'm going to pay. And the reason we let the depositor actually choose that time is that the notion of time on L2 is kind of whack. There isn't like a proper block.timestamp the way there is on L1. On Optimism, for example, the block.timestamp only updates when Optimism synchronizes with ETH L1. So that means there's like this 6-minute interval where the block.timestamp actually doesn't change. So we can't rely on that as a useful means of actually figuring out when the deposit happened on L2. We need some other mechanism to do that. And the second thing is also this enables the user to specify when they're like what block they want to look at, and that way they know the fee that they're going to be paid beforehand, which we think is like quite important. Because if you don't do it this way, then next thing you know, your fee, you think you're going to pay 5% and it ends up being 30%. So this way you can like have more precision and actually understand exactly what you're going to be paid or what you're going to be paying. And go to the next slide. So there's a bit of math here that Chase put together, which we can just quickly go through. We don't need to get like too deep into it. The main things that matter are that the actual equation that calculates the rate is a function of the utilization before the transaction and the utilization after the transaction. So that's UT and UT hat. And the model that we use has this U bar, which is a kink in it. When we'll look at a graph of what that looks like later. And that's exactly the same as Aave. So the graph is basically split up into two parts, like one part before the kink, which is like the costs are low. And after the kink, the costs start ramping up quickly as a function of utilization. And then we have these three magic numbers, R0, R1, and R2, which basically donate different behavioral characteristics of the curve. And these variables, when we actually come to writing the UMIP for a cross, or for the is cross domain bridge valid, that price feed we looked at earlier, these variables will be codified in that UMIP because they define the costing structure of actually moving funds across the bridge. So basically we take these numbers, we put them into an equation, and we get that equation there, and we'll look at what that looks like. It's basically like a straight line with a kink in it. And then to calculate the annualized rate, we just find the area under this curve. So we integrate between the utilization before your deposit and then the utilization immediately after your deposit. And then convert that into a rate over a 1-week loan, which is the equation at the bottom. So you can go to the next slide. So this is basically what that looks like visually. So R0 is like the offset at 0 utilization. U bar is the kink. R0 plus R1 is the rate charged at the kink. R0 plus R1 plus R2 is the rate charged at 100% utilization. So you can see, depending on what the pool utilization is, number go up in APY, basically. You can go to the next slide. So the question becomes, given a deposit that runs from UT of 75% up to UT hat of 80%, so before your deposit, utilization of 75%, then afterwards was 80%. Effectively, what we need to do is find the area of that blue rectangle, and that's the APY that you will pay in your specific deposit. So we could do this analytically, like evaluating that definite integral over that range, but there's also like a geometric solution, which is a bit simpler to reason about. So you can go to the next slide. Basically, we can split this up into some triangles and some rectangles, and then calculate the area at UT, then calculate it at UT hat, and subtract UT hat from UT, and you get the area between UT and UT hat. So that's basically how the bots calculate the actual fee that's going to be charged. And one thing that I didn't really mention so much earlier, but we can quickly talk about it now. The way that this number, this realized LP fee actually gets on chain is that when the relayer brings the deposit information on chain. So Nick, if you can go back to like one of the slides that had the diagram on the bridging action. Yeah, this one. So you'll see in this, the bottom variable in relay deposit is this realized LP fee %, which is the thing we just described now with the graph. So the relayer basically makes a statement about what that number is. The depositor doesn't influence that at all. And the reason we do this is that the depositor doesn't actually know necessarily what the prevailing utilization is going to be at that quote timestamp. They might know what it is because it will be some time in the past, but we can leave the onus on the relayer to actually calculate that. So they can go look back at that timestamp, at the quote timestamp, and then calculate at that block number, this is what the utilization was. And then given the size of the deposit, this is what the utilization would be after the deposit. And then basically pop those numbers into an equation and get realized LP fee percent. So by the relayer bringing it on chain in this way, we can use the optimistic oracle to actually verify the correctness of that statement. And then the disputer bot will go and recompute, like at the quote timestamp that the depositor specified, does the realized LP fee percent map to what the relayer claimed that it is? And obviously we need to verify that because, as with all the other fees, because the relayer could introduce some error in this to try and game the system or steal money from the depositor or from the LPs or whatever. So yeah, that's basically how that number gets on chain, is the relayer calculates it and then it gets verified by the optimistic oracle. Okay, so you can go back to the LP slide. Okay, so we've kind of indirectly spoken about the liquidity providers, but not mentioned kind of what they can do and how they act in the system. So there's only really two things that they can do. They can add liquidity and they can remove liquidity. When they add liquidity, they send in pooled tokens, so USDC or whatever the actual bridged asset is, and they get sent back an LP token. And when they remove liquidity, it's the opposite. So this is the same as it would be if you were adding liquidity to Uniswap, except we're only adding one token. So maybe it's better to think about it as a C token in Compound, where you add in DAI and you get back C DAI. And the mechanism in which this C token actually operates is very analogous to how Compound works. We have an exchange rate in the contracts that represents how many C tokens or LP tokens are redeemable for pooled tokens. And that exchange rate will move as fees are accrued to the LPs. So as more bridging actions happen, as more realized LP fees are actually realized, so the exchange rate will go up. And that means that if you deposit at the very beginning, when the pools are just launched, then that exchange rate will be 1. And over time, that exchange rate will increase. And after time, you'll be able to pull out more money than you put in effectively, which is the accrual of bridging fees. You can go to the next slide. So one element to think about with this is like, how do we actually attribute those fees to the LPs? And the reason you need to think about this is because when you move the funds from L2 to L1, there's like this step action where we go from having the pool liquidity and then at time T, and then at time T plus 1, you have the pool liquidity plus the relayed amount and all the fees, right? There's not like a gradual transition. There's like this stepping function that you would see in the pool balance. And that doesn't necessarily represent the cost that the LPs are taking on. So what we do is rather we kind of stretch or spread the fee payment to the LPs over a period of time. So when we spoke earlier on about the 1-week loan, what you can see is that Across is effectively facilitating the swap like we discussed before, where the depositor is paying this fixed amount and then instantly receiving liquidity, and the LP is instantly providing liquidity and then in a week's time is receiving that deposited amount, including the fees. So what we're doing by stretching this fee is basically, rather than paying it all out once it goes over the canonical bridge, we're saying, let's pay out the fee gradually from the moment of relay until some point in the future. And this has a number of advantages, least of which is that it makes it much more difficult to manipulate this kind of system. Because if you didn't have this stretching behavior, what you'll observe is as relays actually finalize, the exchange rate will step up and it'll keep stepping up every time money comes through. And you could potentially do that to like add liquidity right before the step up and then pull it out right afterwards. And you can basically net that. You'll know that there's going to be like this price action on the exchange rate. And also there could be some like weird stuff that you could do with manipulating the pools to try and like artificially lower your rate for a large bridging action. as well as like a number of other like ways that you can game it. So we basically stretch it out over a longer period so that it behaves more like a normal interest rate. And the way that we've currently parameterized the contracts is it takes about a week for the majority of the fees to be paid out. These are all parameterizable and can be changed by governance. But yeah, that stretching, I think, is like also is a very key component for the user experience when it comes to LPs, right? Because you want to just deposit your money and like watch interest gradually build up. So it can't have any kind of stepping behavior. Hey, Nick?
Yep. Before we go into the next slide, we should, if anyone has questions about the technical architecture, maybe ask them now, because the next few slides are talking more about the future iterations and future features, and also just discussions about where Cross sits within the bridging landscape. I'll also send out the slides right now. Sorry, I should have sent these earlier. They're in the general section.
I'm wondering if we should approve the LP tokens as collateral kind of as we go along, either automatically or in omnibus batches, just so then you could use that to do all of the other UMA tricks with your LP tokens.
Approve on which,
like
L1
to use as a collateral within UMA. So that would be on L1.
I like the idea of bridging the LP tokens. It's like super meta as well.
You could also imagine the LP pool in the future, like acting as a passive manager and not only paying fees to the LPs, but also maybe investing. That's a future version, maybe.
Yeah, for sure. Or if you were paying out KPI options, say you're like a DAO treasury and you want to put like a bunch of your treasury funds in the pools to facilitate bridging, but you also want to pay out KPI options to your users, the KPI options could pay out in the LP tokens. So they'd be earning interest too. So you get like, double utilization out of those tokens instead of them just sitting there. And then the second thing is more of an observation. It's cool to see all of this math getting smuggled in through the yes or no query identifier. So the theory was that like now the optimistic oracle is Turing complete and can do like all of this complex computation, and this is totally doing that. So that's like really interesting to see.
Yeah, absolutely. It's like it's either like 100% correct or there's a marginal error and then it's wrong, right? And that could be like nested within some layers of complexity. So yeah, it's
and not just like it's like the
Sorry.
math, and it's like information from outside too.
Yeah, exactly. It's like the first good example that we've had of that like super generalized like Turing completeness.
Any other questions? Okay.
You guys are, I love the nerdiness. You guys and your Turing complete UMIPs. Bunch of nerds. I love it.
All right. So let's look forward. So again, reiterating one of our original theses is that Ethereum will eventually exist in a world of rollups where the EVM L1 will just be a consensus layer, and a lot of app transactions will get rolled up to L2s. And Across has a really good opportunity to be that bridge between L2 and L1, but also eventually between rollups. L2 to L2 will eventually require an optimistic oracle to be deployed on L2. So that will come eventually, but for now, we're just going to focus on the L2 to L1 transfer. So the way to think about V1 right now, what Chris just described is we are facilitating fast token transfers from L2 to L1, and people who need quick liquidity are going to essentially get loans from people who are willing to wait a week for the slow liquidity. V2 theoretically could ensure just generalized L2 to L1 messaging. So we don't just have to transfer tokens. Transferring any message between L2 to L1 faces the same problems as the token transfer. it still needs 7 days to bridge messaging from a rollup to L1. So a cross could serve as just a general message bridge. You could, yep.
No, I was just gonna give an example. So I had this idea the other day with my girlfriend, where basically the big issue with NFTs right now, or NFT drops, is the auction mechanisms are like super gas intensive, and like just becomes, everyone gets sort of boxed out of the market, right? Like they're super expensive. It like destroys the whole Ethereum network for a couple of hours afterwards. So what happens if you could run the auction, the actual sale on L2, and then let the minting happen once the dust is settled, like a couple hours later on L1? So the way you could do that is you basically tell your users to get some ETH onto L2, or you could pay for them on their behalf using meta transactions because it's so cheap. You run this auction, whatever kind of auction you want, Dutch auction, reverse price auction, doesn't matter, some sale mechanism on L2. And maybe it's like attributing, it could be any kind of sale really, but it works particularly well with NFTs. Then at the end of the sale, once it's finalized, you basically create like a Merkle tree, and you use the optimistic oracle to make a claim about the root of the Merkle tree on L1. And if that gets through liveness, then people on L1 can then go and claim the NFTs that they won in the auction on L2. So this is obviously just like a specific use, a specific application, but like we could build that like quite easily given the tooling that we've built now, and it would solve like an immediate scalability problem that Ethereum is having. And like no one else has that kind of bridging infrastructure where you can bring over like this and this kind of hash, this like Merkle root could encompass like many kinds of applications. So yeah, I think that those kinds of structures are like super exciting to build out into the future.
Yeah, so that concludes the main discussion. And now I thought one thing to talk about would be, where does a cross sit within the blockchain bridge taxonomy? John shared a really good link that sort of, it's a good way of thinking about the different types of bridges. And I wanted to attempt to contextualize where the cross sits. So high level, there are 4 different types of bridges. There's an application specific bridge. This might be something like MakerDAO's bridge or Compound Chain, which facilitates a very specific type of application, cross-chain. So lending markets cross-chain. The opposite of this would be something generalized, which is where a cross can differentiate itself, where we can just transmit any sort of message between chains. And then there are more asset-specific ones, asset-specific bridges and chain-specific bridges, which are optimized for a very specific asset. So say MakerDAO's bridge is going to be from Optimism or Arbitrum to L1, and they can facilitate this because they control the DAI currency. So they can front people instead of needing a pool of LPs to facilitate the transfer. Another way to think about the different bridges is how the transactions actually get validated. So say if you're a depositor and you want your funds to get sent from L2 to L1, who actually secures that? Is it maybe a fixed set of validators, commonly known as a federation? Is it an open pool of validators where anyone can propose or anyone can relay? I think that's where we sit. Another example of security are light client and relay contracts. So this is sort of what Seller, I believe, is going for, where you deploy a contract to each chain, and the proofs are actually computed on chain. The proofs are computed on chain, and this is trustless compared to validators, where you're trusting some set of validators. The problem is you need to deploy a contract for each chain, and that doesn't scale on the development cost side. And then finally, there's a liquidity network, where you don't need validators, you just need people to provide liquidity on both networks. So this is where Hop protocol is offering. And finally, the last taxonomy is security. So is the bridge completely trustless, or is it secured by a bonding or insurance mechanism? And this is where I think the cross sits, where there's an open set of validators who can relay transactions, but they're economically incentivized to behave correctly. And the last set of bridges is a trusted bridge. So something like Binance or Coinbase, where you can cross chains, but you're just completely within a closed garden. Does anyone disagree with that? Agree with that? I'm not entirely sure, but that's where I think we sit.
I think there's a lot here to discuss and figure out, Nick, and like a lot of potential uncertainty. I was talking about this a little bit with Matt yesterday too. I think that there's a broader concept that we are potentially working towards that we don't have all figured out yet, which is this idea of using an insurance concept to enable like cross-chain, cross-shard, or cross-rollup communications. And I think it's actually, that's a kind of, this is maybe like a bigger picture way of saying where we might go with this too, where instead of using like all the other networks of having this like federation of validators to validate that something happened, this is using this insurance concept to ensure that something happened. So it's like not fully baked yet, but I think that there's this nice progression here where we try to really win at L2 to L1, like we do that really well. And then maybe we do cross roll-up stuff really well. And then maybe in the process, we can actually develop this insurance concept to do all this other shit too. What do you think?
Yeah, I think like the clearest distinction between us and other options is that we delegate most of the computation off-chain, whereas there are some bridges that are going to be very much on-chain. And also we're not a pure liquidity network. We are trusting a set of validators, and if that set of validators are centralized, then we're more of a trusted bridge than not. But I think what's different between us and say like Polygon or is that there's the possibility for an unlimited amount of validators.
Wait, Nick, do you think you describe it as us trusting a set of validators?
Yeah,
I don't think I agree with that.
we do. Well, you're trusting the optimistic Oracle validators.
Are you? I mean,
Well,
like,
if someone puts in a bad relay and there's no other relayer to dispute it, then that will succeed and the relay will go through.
well, then I guess what I'd say is like, we should make the dispute function easy at a future version.
It's just,
Right.
you just dispute with the optimistic Oracle.
What do you mean?
Like if you want to dispute a relay, you go directly to the optimistic Oracle.
I'm a bit like, just very conceptually, Nick, I want it like the way we ensure this or make this be very trustless is like, hey, I'm trying to send my money to L1. It didn't show up on this time frame. I'm disputing it. Cool. Right. And like, this is zooming away from like the low level engineering of it. But in theory, if like that functionality existed, which it could exist, then I'm not trusting anybody. I like, you know.
Yeah. I mean, I think ultimately it's like relying on some liveness assumptions. But yes, you do at the end of the day have like the UMA market cap. It's the basic assumption we always have with all of our stuff, right? Like it's as the trust assumptions are the same as any other UMA product, right? There's no weaker than like liquidations in an EMP or settlement on an LSP. Like the trust assumptions are the same.
Well, we're just saying screw like all the DVM trust assumptions. We're just saying like there's a concept here that's different from a validator network where you have to trust that validator network. Here, what we're trying to say, and what I'd like our messaging to be consistent around, I think, is like, hey, I can dispute whether this thing actually happened. And if we make it so that the user is able to dispute, like imagine we had a third tab in the UI that's like literally like the dispute tab. And then a user can be like, okay, I'm disputing this because my thing didn't show up. Then I think like conceptually, that's like a very strong premise where we're like, you're not trusting anybody here.
And I think in that scenario, if like the money is just not showing up that quickly, the user can come in and just go and get the money, or like anybody can go and like execute the relay. So I'm not sure if that's like a dispute within the system so much as like the user went and got, you know, some money for gas to do the slow relay themselves, kind of, or like got somebody else to do it, because the money's always locked up ready for them whenever they want to go get it. It's just nobody triggered the relay that quickly.
There's a lot of nuance here that I think gets lost when we talk about like the actual engineering decisions, but like, just so you guys know, like when we're like up on stage describing this thing, I want us to be able to say, at least like in kind of concept, that's like, hey, who are you trusting here? Well, it's like nobody, right? You are ultimately trusting that the DVM works. Like, yes, we are trusting that. But in terms of trusting a set of validators or relayers, the idea is that you don't have to trust them because we have this dispute process, I think.
Yeah, which is open and anyone can participate, including the person that's doing the bridging.
Yeah. And there's something, again, that's actually quite powerful for even how we sell the optimistic oracle here, which I think Sean is having some success with too, where we can go through this, we can basically say, hey, you guys want to do something in like what otherwise looks like a highly centralized way. And this would be like, I mean, in essence, you have one relayer node or you're doing this one thing. You can do it in a highly centralized way, but actually make it trustless if there is an ability to dispute that. I think that's really cool.
Yeah, I think you can say that part. I think you can say it is trustless, and we could totally expose a dispute button on the front end.
I think
Yeah.
Melissa
Melissa.
raised your hand. Melissa?
I heard your mic was on, but I didn't hear your question, Melissa. Can anyone not hear Melissa's?
Yeah.
I can't hear.
Yeah. I think it was a mistake. Okay, are there any other questions?
Just an observation. I'm thinking through like how people might use this, and one thing we don't bring up a lot is that you can self-relay too, and that kind of came up in the last conversation. But it might be something to like highlight, like if you have at least like self-relay like the slow way.
Yeah, you could deposit, and then you could immediately like flag a relay, and you don't have to provide liquidity up front. You'll have to post a small bond. Yeah, I think that's possible.
It would be pretty easy to add to the front end as well, like in a future version. If your thing, like it's kind of like self speed up. The bond is a bit of a UX hurdle though, right? Because you need like the token you're relaying in your wallet to post the bond, which is not ideal. But
yeah,
but yeah, you could like
self
self speed up.
Because you have, that means some of the asset on L1 that you're trying to relay from L2 to L1, but maybe not enough.
Not ideal.
yeah. So that might be more of like a professional thing though, if you're like shuffling funds around between chains and you're okay waiting a couple of hours because, you know, then you can do slow relays like that.
Also, if you're like, I can imagine there being users that set their rewards to 0, like both the slow and the instant reward to 0 with the intent of them slow relaying it. that could also be possible, where like you don't actually want to pay anyone, but you want to use the service, then you'll only pay the LP fee, the realized LP fee.
Would that set like a disputer's reward to 0 as well?
No, because the proposal, when you do the slow relay, that includes the disputer reward. It's just there's no
Gotcha.
reward to the actual relayer because you are the relayer. Like you could also quite easily create a relayer bot that only relays your own messages, and then you always just set them to 0. Like that I mean, I don't know if that's even like that big of a issue, because like the LPs are still getting paid. Like there might actually be some like power users that take advantage of that.
Something I just thought of is, could you use this bridge as sort of a way to privately like seed an account on L1? Like, could you?
Yeah.
Mm,
I think so,
so
yeah.
almost.
Yeah.
I mean,
I don't see
you
why
can
not.
see though, you can see the origin of the funds on L2 though, right? So
But that could just be privacy provider, maybe some pool of funds, and you pay them a fee or something, and then they'll seed your account.
that's interesting. Yeah, you need to think about like that privacy provider, like how they can break the link. But yeah, that's a very interesting one, because you can also like seed exact amounts, right? Rather than like these amortized things in Tornado Cash. So yeah, that's cool.
Could I just ask who the anticipated users of this would be? Is it kind of envisaged that it would be individuals using it, or that it would be protocols using it, or that protocols would kind of integrate it into a larger product?
I think for me, like hopefully all of the above, but an example that I'll give that I think is like recently an example that we can draw from, which might give insight into what our user group would be, is like there was this non-cat yield farm on Arbitrum that attracted like $1 billion of TVL in like a couple hours, and the yield mining stopped on that like a couple hours ago. It was literally earlier today. And there was this whole Twitter discussion around, okay, so what happens with that liquidity? Like, does it go and find other yield opportunities on Arbitrum? And the overwhelming consensus was, no, it's probably just going to leave Arbitrum and go back to L1. So those users would very likely use a service like this, right? Like they were chasing yield, they got onto the yield onto the L2 quickly, and then they need to exit quite quickly. So like as a user group, I think it would be that. And obviously, like ideally, we have protocols integrating with us directly, right? Like if you have like maybe there's like a matcha or a 1-inch for bridges at some point in the future, there's like any swap and like some other stuff that Jörn's working on. I don't know. Maybe there's like a way in which this can be part of like an aggregator, and also like directly integrated into protocols that are cross-chain.
Thanks, Chris.
Any other topics that people wanted to discuss? Otherwise, we're officially over time.
Really cool, guys. Well done. Thanks for this.
Thanks, Art. Cool. All right, let's wrap up. Thanks everyone for
Thanks,
attending.
Nick. Thanks.
Yeah, this was awesome.
Amazing. Thank you, Nick. Thank you, Chris.
Just to say that we've got a slot for the internal learning session next week. If